already know what real numbers are. These are the numbers that can be represented on the number line. We also know that real numbers can be broadly classified as rational and irrational numbers. Rational numbers are those that can be represented as ratio of two integers with no common factor. Irrational numbers, on the other hand, cannot be expressed as ratio of two integers, and when expressed in decimal notation, they are non-terminating, non-recurring decimals. Are there any other kinds of numbers? Numbers that we haven't looked at yet? Before you answer that question, let me ask you another one. Can you think of a number which when squared results in a negative number? Yes, a number which when multiplied with itself gives a negative number. Try it. You'd have probably tried a few options. 3 times 3 is 9, positive. Negative 5 times negative 5 is 25. Again positive. Negative root 3 times negative root 3 is 3. Positive again. No luck. We'll come back to this. Don't worry. So we've studied quadratic equations in middle school. We know that if x squared minus 9 is equal to 0, x is either equal to 3 or negative 3. Now try to find a solution to x squared plus 1 equal to 0. Not sure? Or do you think there's no solution to this one? Don't worry if you couldn't get the answer to these two questions. Let's understand the situation now. Whenever we considered the square of a number, say x, the result was always positive, whether the number x was a positive real number or a negative one. We always got a positive result. And we had learned that a negative number did not have a square root. So if we had a number like negative 9, we said that its square root did not exist. Do you remember that while finding the solution of a quadratic equation using the formula, if the discriminant b squared minus 4ac was negative, we said that there are no real roots of the quadratic equation. Based on what we had studied earlier, x squared plus 1 equal to 0 will not have any real roots as the value of discriminant is negative 4. Why did we do this? What was the problem here? It's easy. As the square root of negative 1 did not exist for us, we said that there was no solution for the equation x squared plus 1 equals 0. However, in the 16th century, it was a mathematician named Cardan who first started thinking about solutions of quadratic equations with negative discriminants. Soon, others started too, but it was Euler in the 18th century who gave the square root of negative 1 a symbol I and called it the unit imaginary number. These were termed so as they were thought to be impossible and just something we imagined. So I was assumed to be a number whose square is negative 1. Now you'll be able to answer the two questions. Can you think of a number which when squared results in a negative number? Yes, it's I. If square root of negative 1 is I, what is I times I or I squared? It is root negative 1 times root negative 1. That gives us negative 1. There you go. We got a negative number by squaring a number. And the next question was, can you find a solution to x squared plus 1 equal to 0? The answer is yes. Transposing 1 to the right-hand side, we get x squared as negative 1. Taking the square root on both sides, we get the value of x as root of negative 1 or minus root of negative 1. That is plus minus I. So what we learned in school wasn't incorrect. This equation has no real roots. Yes, it has imaginary roots. That's the concept of imaginary numbers for you. But wait, we understood the concept of square root of negative 1. What if the number is square root of negative 7 or square root of negative 9? That's what we will cover in the next video.
क्या आप जानते हैं कि अब आप डाउटनेट पर आईआईटी जेईई की भी तैयारी पूरी तरह से कर सकते हैं। मान लिया मैं पढ़ रहा हूं और
In the equation, we understood the concept of a unit imaginary number I. It is the square root of -1. If we square it, we get root of -1 times root of -1, which equals -1. The square of the unit imaginary number is -1. Well, let us now try to work out more powers of I. What will be I cubed then? Try it out. I cubed is I times I times I. We can write it as I squared multiplied by I. Now, as I squared is equal to -1, I cubed is -1 multiplied by I, or -I. So the value of I cubed is -I. You can now similarly work out fourth power of I. Give it a try. The fourth power of I can be written as I squared multiplied by I squared. This is nothing but -1 multiplied by -1. And we already know that -1 multiplied by -1 is 1. Hence the fourth power of I is just 1. So I squared is -1, I cubed is -I, and fourth power of I is 1. Can you similarly work out further powers like 5th, 6th, 7th and 8th powers of I? Try it out and you will observe something interesting. And this is what we would get. Notice the cyclical pattern in the powers. I, -1, -I, 1, and then again I, -1, -I, and then 1. This is one way in which we can understand it. First power, second power, third power, and fourth power. Then repeat. Fifth power, sixth power, seventh power, and eighth power. And this will go on. So what is I? It is just a unit imaginary number and is equal to the square root of -1. Why do I keep saying the word unit? To understand that, let's look at an example. What will the square root of -9 be equal to? If we try it out on a non-fancy calculator, it would say that the input is invalid. That's because most calculators are not programmed to use imaginary numbers. So how do we understand the square root of -9? It can be written as square root of 9 times -1, right? And we know a property of exponents which says that square root of a times b is equal to the square root of a times the square root of b. So this can be written as square root of 9 times the square root of -1. The square root of 9 is 3 and square root of -1 is I. So the square root of -9 is 3i. This is 3 times I. And this is also an imaginary number. But it's not a unit imaginary number as it's 3 times I. But the unit number I is 1 times I, and hence it's called a unit imaginary number. Basically, any real number times I is an imaginary number. For instance, this is how we would write square root of -121 over 49. We get 11 over 7 times I. It's a real number times I. So numbers like 0.145i, 16.25i, minus cube root of 7i are also imaginary numbers. An imaginary number is simply b times I, where b is a real number and I is the imaginary number. So if tomorrow morning, what if your dad asks you, are imaginary numbers real? How would you answer that question? Well, it's a tricky question. You should tell him that imaginary numbers are not real numbers. They cannot be plotted on a real number line. But they are real in the sense that they exist in mathematics and are used widely in various applications. What kind of applications? We'll see that next.
मेरी छड़ी उठा दोगे?
In the previous videos, we learned that it is possible to have square root of a negative number, but it involved using a new number I, which is equal to the square root of -1. These numbers are called imaginary numbers and could be of the form bi, where b is a real number and I is equal to square root of -1. Numbers like I, 2i, -4i are all imaginary numbers. What if we have a number like 3 plus 7i? Will this be an imaginary number? Well, we can be sure that this part of the number is imaginary and this part is a real number. So this is a mix of real and imaginary parts. And this is what we call an example of a complex number. Real plus imaginary gives us a complex number. It's of the form a plus bi, where a and b are real numbers and I is the unit imaginary number. Now let's play around with this basic form. Observe that when a is equal to 0, what is left will be an imaginary number. And when b is equal to 0, we only have a real number. So what are the real and imaginary parts in the basic form of a complex number? A is called the real part and bi is called the imaginary part. Now let me ask you something interesting. When will the two complex numbers a plus bi and c plus di be equal? They will be equal only if both the conditions are satisfied. First, a is equal to c and second, b is equal to d. Yes, only if a is equal to c and b is equal to d will the two complex numbers be equal. Real parts equal and the imaginary parts as well are equal. However, though real numbers are comprehensible, why are we moving towards complex numbers? Do they lead to anything worthwhile? There were doubts about it, even among mathematicians who initially developed this concept. While some did not believe in them, others were desperately trying to prove their existence. Still, the journey continued and complex numbers were finally allowed by mathematicians. Today, though most people may find complex numbers incomprehensible or difficult to understand, they do exist in some form and serve the purpose of understanding of nature. Engineers use it to study stresses on beams, phenomena of resonance, and the flow of fluid around objects such as water around a pipe. They make it easy to understand the flow of current through electronic circuits using resistances, inductance, and capacitors. They are also used in electromagnetism, where rather than trying to describe an electromagnetic field by two real quantities separately, they are described as a single complex number of which electric and magnetic components are simply the real and imaginary parts. How exactly are they used here? Well, it's an advanced topic which we will cover in our graduation level math videos. It's easy to plot a real number on a number line, a real number line. For instance, the number 3 can be plotted here. The number -4.5 can be plotted here. But what if we have an ordered pair of real numbers? Something like 2, 3? How can we represent this on an xy plane? 2 units on the x-axis and 3 units on the y-axis gives us the point 2, 3. This point P had an x component and a y component. Now look at the complex number 3 plus 4i. This number has a real part and an imaginary part. What if we want to plot this on a plane? How can we do that? A good idea would be to assume the x-axis as the real axis and the y-axis as the imaginary axis. So based on this, we can say that this complex number corresponds to the ordered pair 3, 4. 3, the real part, and 4, the imaginary part. Remember, the horizontal axis is the real axis and the vertical axis is called the imaginary axis. So 3 units right on the real axis and 4 units up on the imaginary axis will give us the position of the complex number on this plane. To plot the ordered pair of real numbers, we used the xy plane which had real numbers on both the axes. Do you remember what that plane was called? Yes, the Cartesian plane. And these coordinates were called the Cartesian Coordinates. What is this plane called then? The plane in which the horizontal axis is the real axis and the vertical one is the imaginary axis. It's called the Argand Plane or the complex plane. It was Jean-Robert Argand who is credited with development and elaboration on geometric representation of complex numbers and operations upon them. This assured him a place in history of mathematics by calling his representation of complex numbers on a plane as Argand Plane. A complex number z is equal to a plus ib is simply written as a comma b, and this can be represented on an Argand plane. Now, what if the points lie on one of the axes of the Argand plane? Say the point is here on the x-axis. This number will have only the real part. It can be written as 5 plus 0i, and if the point is here on the x-axis, it will be negative 3 plus 0i. And what if the point is here on the y-axis? Every point on the y-axis will have only the imaginary part. So this point will be 0 plus 4i. Every point on the x-axis corresponds to a complex number of the form a plus i0, and every point on the y-axis corresponds to complex numbers of the form 0 plus bi. So as an exercise, let's try to plot the following complex numbers on the Argand plane. We will see the solution in the next part of the video.